Good afternoon to you. This is Module 7, Lecture 38. We are starting a new topic, a new module, a rather advanced topic. It's called Analysis of Elastic Instability and Second Order Effects. So we are at the home stretch. We have 3 more technical lectures on this topic. Quite frankly, this is normally not covered at this level, but if you don't cover it now, you'll probably never get to cover it. So I would like you to have the benefit of relaxing, sitting back and listening and trying to absorb some basic concepts in an advanced topic. Okay. Up till now, up till the 6 modules, we have really covered how to do from first principles analysis of skeletal structures of any type, of any dimension, 1-dimensional, 2-dimensional, 3-dimensional. We now look at what happens when you have nonlinearity. Okay. Till now it was all linear elastic analysis. So a glimpse of some aspects of nonlinearity is covered in this topic, plus we look at an interesting phenomenon called elastic instability, otherwise popularly known as buckling. So you've studied a bit of buckling, Euler buckling. So okay, so we'll refresh all that. So there are 4 topics we'll cover in this module: an introduction, effects of axial force on flexural stiffness. We will cover these 2 topics in this session. In the next session we'll cover slope deflection method of analysis modified to include second order effects, and in the last lecture we will cover matrix methods of analysis. Okay. So this is covered in the last chapter in the book on advanced structural analysis. We will now look at the problem from a design point of view. See, what we are attempting to do is to predict structural behavior, assuming certain properties, and conveniently in practice we assume linear elastic behavior because it's very easy to do, and we can happily apply the principle of superposition. We can apply the effects of different loads, find the responses for each of the loads, we can apply factors to these loads, and we can do superposition under combined effects. Okay. So dead load we do, live load, wind load, etc., earthquake load. But the reality is, when the loads are significant, or when the structural elements are flexible, you get into nonlinearity, and nonlinear analysis can be quite tricky, and we are not guaranteed of accurate solutions. But regardless of what you do, it's well known by experienced engineers that if you satisfy certain requirements, minimum requirements, you will end up with a safe design. So what are those requirements from a design point of view? The structure should be able to carry its design load safely if 3 requirements are satisfied. Let's look at them. Firstly, you must satisfy equilibrium. Okay. The calculated system of forces must be in equilibrium with the loads and reactions throughout the structure, should not violate equilibrium. Secondly, every component must have adequate strength to transmit the calculated force. So you get something from analysis, you get a bending moment, your beam must have that bending moment capacity. That should not be exceeded, otherwise your equilibrium solution is not valid. Secondly, even if you have nonlinearity in the form of yielding here and there, you have to make sure that the structure remains integrated, that you have possibly the formation of plastic hinges. You studied about plastic hinges, and you must have enough plastic rotation capacity so that the hinges hang on, and that that is related to ductility. In reinforced concrete especially, it all depends on your design of those sections so that you have this plastic rotation capacity and you have adequate ductility for that hinge to stay on resisting a certain ultimate moment and redistributing the load effects to other locations. Okay. So this is something that has to be ensured, and finally you must have enough stiffness to keep the deflection small. Okay. Because if you have very large deflections, the structure becomes unserviceable. In an earthquake we do not mind for less important structures because we want to prevent collapse, and the structure may be badly damaged, but we give up the structure, but we hope that life is safe. But for lifeline structures like let us say hospitals and so on, we would not even want that. So we would want functional behavior even under extreme events. So their stiffness is of paramount importance. But we also should avoid instability. Okay, we have to avoid buckling instability, and this can be elastic instability, it could be inelastic instability. So it's a very complex problem. We are going to have a glimpse of elastic instability. You must have studied when you do trusses, you have this double bracing, right, the cross bracing, and when the wind blows, one of those diagonals which goes into compression is expected to buckle, and so the other one which is in tension will operate. But because it is in elastic instability, it bounces back after the wind has blown back. It is still effective, and if the wind were to blow in the opposite direction, it will now go into tension and function. So in trusses, really in pin jointed frames, you have only component level instability. Okay, so you are very sure the length is known, and then whatever little you have learnt of instability in local members is good enough. But when you talk of system, let us take a portal frame, rigid jointed portal frame, and if let us say the column buckles, then that rigid joint will ensure that the beam will also buckle and the rest of the structure will also buckle. So it is a very complicated analysis. You understand? You have a global instability taking place. You can't separate local with global. Local is possible only if both the ends are pin joint. So we are going to look at those kind of problems in continuous beams and in frames, multi-storied frames, where you have this possibility of buckling, which you must necessarily avoid if you want to have a safe design, because you can have a disastrous failure of that structure. So what is the level of loading that will cause such an instability, and how should the structural analysis be modified when the stiffness is low? When the stiffness is low, you will have second order effects coming in. We will look into that. They are called P delta effects, and usually when the deformations are large, you will also generally encounter material nonlinearity in addition to geometric, but we will keep that aside for the time being because it depends on the type of material. Right now we are looking at elastic behavior, and we assume the material really does not matter. Once you have the E value of the material, we can go ahead with our analysis. So nonlinear structural analysis is called for when there is significant material nonlinearity or geometric nonlinearity. In this module we limit considerations to aspects of geometric nonlinearity in frame elements, and this is related to slenderness effects. We need to account for the reduction in flexural stiffness in beam column elements due to axial compression, and we briefly looked at this earlier. If I have a beam, the flexural stiffness is either EI by L, 3I by L, 4EI by L depending on the boundary conditions, but those values will reduce if I have axial compression acting in that element, and those values will increase if instead I have axial tension. So we are looking at that behavior. It may not be of concern if your level of axial loading is low in relation to the buckling strength. So I have suggested there that as long as your axial compression is less than 15% of your critical buckling load, perhaps you can ignore this in engineering practice. But when the axial compression level is high, then it has a major effect in dictating your response. You will be underestimating your response if you ignore the interaction between axial stiffness and flexural stiffness, which we do in the normal frame analysis. Remember, we write EA by L and we put zeros, and we write 12 EI by L cubed. All that will change when there is a coupling between the axial compression and the bending. Okay, and so we call such elements beam columns. So we are going to look at those kinds of behavior. You see, when I have a beam column and I say the flexural stiffness is 4 EI by L, if I apply a axial compression P, till now we have assumed that 4 EI by L will not change. It can change. It depends on P, and if P is as high as the P critical, the buckling load capacity for that element, what do you think the flexural stiffness will? It will degenerate to 0. But if it is less than 15% of the critical buckling strength, then the degradation in 4 EI by L may not be very significant. So you have to take a call whether to do nonlinear analysis or not. So definitely you should look into nonlinearity when the 15% is exceeded. Is it clear? So that is what we will look at, and we will also look at a modified slope deflection method and matrix method, which can do two things. One, tell us what is that critical buckling load in the frame where it becomes unstable. Number two, even if the loads are less than that, what is the correct solution? How much does my bending moments, shear forces, deflections get amplified because of this reduction in stiffness caused by axial compression? Is it clear? And there may be instances where you have axial tension, where your stiffness actually gets enhanced and your deflections become actually less. So let us do a quick review of something you already know only too well. If I apply an axial compression in a column like that, which is free on top and fixed at the base, do I get any lateral deflection? This is an ideal column, which I will not until I reach its critical buckling load. So how do I find out that critical buckling load? Let us go through first principles. How do I find out? Well, I assume it's happened, because in practice it's going to buckle at some point. And then what do I do? Assume a shape and
find the
moment at any section and satisfy equilibrium related to the deflection. How do I relate bending moment to deflection? Curvature is
M
by EI, and curvature is d squared delta by dx squared. Okay, so that is what you do. So in a cantilever, the first mode of buckling is typically going to look like this, and you could solve this equation. We will look at it in the next slide, but you can work out the critical buckling load for a cantilever. If both the ends are simply supported, then you will have a different profile. Now this is what can happen at that point where P is touching on P critical. You hit what is classically called a bifurcation point. Why is it called a bifurcation point? Because at that loading, mathematically, two equations of equilibrium, two states of equilibrium are possible. If you remember, this is an eigenvalue problem. In the eigenvalue solution, you have two solutions. One is called a trivial solution, where delta is 0, the other is a non-trivial solution, right? Yeah, so both are satisfied by the same equation. So you have two possibilities. If delta is 0, that means it remains straight, and if delta is not 0, it means it buckles. Is it clear? That's the whole, that's the beauty of the eigenvalue solution. Got it? So in practice it prefers to buckle, it won't remain straight, and the solution that you get predicts actually no limit to the deflection, right? It will go on deflecting. The eigen solution, the eigen function or the eigenvector if you are doing a matrix analysis, only tells you what is the shape. Is it a sinusoidal shape, etc. It only tells you the shape, it does not tell you anything more than that, which means it tells you, let us say, the mid height of the column, what is the deflection in relation to the top. Those ratios are maintained. That is what we call a mode shape, and the first mode shape looks like this. You can get another solution to the eigenvalue problem at a higher mode, which will have a node and so on, but that is unlikely to happen because once it is failed in the first mode, there is no question of it failing in the second mode. But in reality, it will not follow this horizontal line. Can you tell me why? It could follow this line, which means you have a post buckling strength, or it will go down, where you usually, when you have, when large deflections are there, you will have material nonlinearity also coming in, it can go down. So why is this theoretical prediction of that horizontal line not valid in real practice? No, mathematically. And the classic example given is, you have seen these pictures of Charlie Chaplin leaning against a cane, right? The cane, the more he leans against it, the more it buckles, but it does not have an indefinite deflection. It is related to the force he is applying, right? So although he is buckled, it is buckled, the more he applies, so there is a unique solution for every load he is applied, which you will get from that yellow line. Got it? So it makes sense, that is called post buckling strength. Why does it happen? Why is it that mathematically you are not getting, you get an eigenvalue problem in which that should not happen? It is an old question. Yes? Okay, the answer is, we are making an assumption, when we say curvature is EI into d squared delta by dx squared. That assumption is valid only when your deformations are small. When your deformations are large, you have to take the other form, remember 1 plus and with raised to 3 by 2. If you do that, you do not get an eigenvalue problem. And if you do that, you will get that yellow curve. So these things are well known. So that is called large deformation analysis, which you do not normally study at an early level. But in elastic stability, you get a solution like that. Okay. Now if the two ends are simply supported or pinned like this, the buckle shape will look nicely symmetric. And this is a standard case which actually Euler explored, and this is called the Euler load, Euler buckling load for the standard case where the solution is pi squared EI by L squared. You are familiar with this, right? Look at that equation. EI is on the numerator, which means if you had a member with a large flexural rigidity, the buckling load will be much higher. And the denominator, it's L is coming into the picture. So if the member is long, then its buckling load is going to be much less. Okay, so these are intuitively obvious, and you can prove for a cantilever it's 1/4 this value. You know this. For a cantilever, it turns out to be, it's obviously less stiff than a simply supported case, so it turns out the buckling load is 1/4. And if you really want to solve this from first principles, you have to write the differential equation of equilibrium. What you said is one way of writing it. The differential equation for equilibrium in a beam can be written as m by EI is equal to d squared delta by dx squared. That is one way of writing, but a more powerful way is going to the fourth derivative and writing it in this way. And if you do not have any lateral load on that beam, we are talking about pure buckling case, then you should put the right hand side is not q of x, it is going to be 0, right. So this is a fourth order standard differential equation. How do you solve this? Well, we first do this substitution, we bring in a parameter mu, which is square root of p by EI, okay, and you plug it into that equation, and you get the mu squared term. You solve it. This is a fourth order equation, so you have 4 constants, typically sine and cos, and you just have to apply the boundary conditions, right? Let's take this propped cantilever case, okay, the third case we are going to look at. What would be the 4 boundary conditions you will apply? At x equal to 0, delta is 0, delta dash theta is 0, at x equal to L, delta is 0, you still need a fourth equation. So these 3 equations are called kinematic boundary conditions. They come from the fact that you have fixity at the bottom end when x equals 0, and you have a restraint against translation at the top end. You need one more boundary condition. Can you tell me what? At x equal to L? No. You're right, the fourth boundary condition will come at x equal to L. Can anyone tell me what that is? What is 0 at that end? Deflection you've already written as your third equation.
Moment is.
Curvature is? Why is curvature 0? Because moment is 0. So that's a tricky boundary condition. That's called a static boundary condition. So when you run out of kinematic boundary conditions, search for static boundary conditions. You will find either the shear force or the bending moment is either 0 or some known constant. So EI d squared delta by dx squared is 0, which means second derivative of delta is 0. So those are the 4 boundary conditions. If you apply them and you plug in the solutions, you can write it in a matrix form. When you solve this, you get some constants for A, B, C and D, and the last equation when you solve will be an eigenfunction, eigenvalue problem, okay, and typically it will take some shape like this. So tan mu L equal to mu L is a transcendental equation. You can have multiple solutions for these. The lowest value of mu L corresponds to your fundamental mode, and that's how you get mu L equal to 4.493 in this example. So this example, that equation tan mu L equal to mu L is called the characteristic equation. You remember when you did eigenvalue analysis, there was something called characteristic equation, and the first mode solution in this case is 4.493, and if you plug in the value of mu, you can get the critical buckling load, which we also call the Euler load, and it turns out to be 2.047 pi squared EI by L squared, which can also be written as pi squared EI by 0.7 L the whole square. So what is this 0.7 L? Yeah, that's your effective length. It's the length between the points of contraflexion. Very good. So you can do that, and you have a reference standard case. We'll denote that as PE naught. P is any Euler buckling load for any boundary conditions in an ideal straight column. Okay, and this is called the effective length. You're familiar with this. So that turns out to be 0.699 L or 0.7 L. So for any given boundary conditions, you can get through such a mathematical analysis where you have 4 boundary conditions, you can get the solution, a unique solution. It's an eigenvalue solution where you can find the critical buckling load PCR. You can express it as a factor times the Euler buckling load for the standard case. In this case, that factor is 2.047. You can also relate it to the effective length. That effective length K, will it be less than 1 or greater than 1? That effective length ratio or effective length factor, KE. When will it be less than 1 and when will it be more than 1? Cantilever, how much will it be? 2. Okay. So can you generalize and tell me under which conditions it will be less than 1 and under which condition it will be? Yes?
When restraints go up,
when the ends are fixed. No, my ends can be fixed, but let's say I have a guided fixed support, this can move. No, so you have to be more clear. When will the, that's obvious. When will that threshold of 1 be crossed? So we'll look at that. You don't have the answer. So similarly for a braced column, for both ends pinned, you know that the mode shape is sinusoidal, this is the standard solution. If you have both ends fixed, you know the effective length ratio is 0.5, and so you get 4 times the standard case critical buckling load. If you have a guided fixed support, it's very interesting, that is the bottom is fixed, the top is fixed, but the top is free to translate. When do you have a case like that? For example, you have, let us say, a water tank structure with a shaft with a solid mass on top, reinforced concrete, or a pile cap on piles. So you get stiffness there, you get a joint stiffness there, but it can move. Nobody is holding that water tank, it can move. So you can model it like that. Okay, so in such cases you will find you have to extend that line to get the second point of contraflexure. It turns out to be L. So this case is called an unbraced case. So we use the word braced when a braced column. How do you distinguish between a braced column and an unbraced column? Yes, Ashish? How do you distinguish between a braced column and an unbraced column? Okay, a braced column is a column in which you do not have any chord rotation. That means the two ends of the column will not have any relative translation between them. In an unbraced column you have relative translation. So the second case is unbraced, the first case is braced. So your generalized expression is given like this, okay. You put LE squared at the denominator, pi squared EI by LE squared, or you can write it as 1 by KE the whole squared PE naught, and you will find that KE is less than 1 for a braced column. When you have both ends pinned, it is 1, when both ends are fixed, it is the lowest value of 0.5, and when you have an unbraced column, you can have any value between 1 and infinity. You will have 1 when you have a guided fixed support at the top and fixed at the bottom. In a cantilever it is going to be 2, and when do you get infinity? If both ends are pinned, it is unstable, okay. So that is the other. Let us say you have a beam, you have a multi-storied building in a column, and the column has pinned ends, that means the beams have 0 stiffness. Then that is asking for trouble because it is going to sway like hell, it will be unstable, okay. So to show you a picture of a column in a building, you need some elements in the building which will which will give the bracing effect. So it usually comes when you give some shear walls, etc. So the building as a whole is prevented from swaying, so every column in that building will become braced, okay. Please listen. Whether a column is braced or unbraced is not necessarily dictated by that column or those beams connecting that column. It is dictated by the whole building, the rest of the building. So if I have, for example, shear walls, adequate number of shear walls which are going to take most of the lateral load, they hold the building together, they do not allow much sway. So because you have floor slabs connected to these shear walls, the framed elements also will not sway significantly, and so in such situations you model it as a braced column. But if you do not have any bracing elements like shear walls, then, and if your columns are not very stiff, then you can have this case, okay, where you have significant sway. In such cases KE will always be greater than 1, but do not have high values of KE because then you are asking for trouble. You will have lots of secondary, you will have lots of second order effects. So when do you have second order effects? Primarily in unbraced frames. Okay, now our real interest is not so much column as beam column, right. So we make our first entry into beam columns by looking at structures like this. Take a look at that, okay, that is a channel shaped structure in which I apply P eccentrically. okay, that value of E eccentricity is called primary eccentricity, right, but the more I press there, the more it will bulge outward, so I get a delta in addition to E. If the column is very stiff, that delta will be close to 0. If that column is slender, that delta is going to be significant. Does it make sense? Okay. Now you can, this is a case where both ends are pinned. If you study this case, you take a free body and write the equilibrium equation, your moment at any section in the deformed configuration. Please note, this is a big difference between second order analysis and first order analysis. First order analysis, we wrote all our equilibrium in the undeformed configuration. In the undeformed configuration, delta won't come into the picture. You will have P into E only. That is first order analysis. In second order analysis, we are writing P into delta plus E, because we are saying delta is no longer negligible. Is it clear? That is the big difference. So when you write this equation and you solve for this, you will find that you have an eigenvalue problem here, which if you solve for, you get an expression. This is called a secant formula, it is a famous formula, and your deflected shape looks like this. Remember the first figure we drew, we had a bifurcation point, right? Okay, we no longer have that bifurcation point. Actually, you do not have an eigenvalue solution. This is not an eigenvalue problem. You have a unique solution, and what is interesting is that all those lines you can see, if you look carefully, if your column is stiff, you are probably going to get this curve. If your column is slender, you are going to move inward. You get it? So it is going to deflect more and more as you apply more and more axial load. But there is no way you can apply an axial load higher than the critical buckling moment of a column without any eccentricity. So you will find all these lines theoretically will asymptotically hit your critical buckling load. Is it clear? This is the difference with respect to the earlier figure. In the earlier figure you had an ideal column, now you have a same ideal column, but we are deliberately putting a primary eccentricity, and these are the curves it will take. Is it clear? You have to know only this much. Now I want to ask you a question. Why is it that that columns buckle, columns do not show that bifurcation buckling even if I do not have primary eccentricity? In fact, it starts showing the deflections very early itself, like this. I have a column, apply a load, actually if I test in the lab, it is not going to remain straight and then suddenly it is going to do that. It is going to give you early warning signs that it is going to buckle. Why? That is called a real column. Real columns give you warning signs before the instability takes place. Why? Because of what? Because of initial imperfections. You can never make a 100% straight column, it is not possible. There is always going to be some initial imperfection. That is what we are going to look at. So if you have initial imperfections, then this is not the solution you will get, because this is for an ideal column. You are beginning with a bent shape. Even that cane which Charlie Chaplin was leaning against always had some bent in it in the beginning itself, right? So that you can't help it. So you will have an initial imperfection. The order of that initial imperfection is something like span by 500 and so. And any material you are bound to get something. We do not know the profile of that initial imperfection. But if you really want a worst case scenario, you can imitate the same fundamental buckling load profile. So in this case you can assume a sinusoidal initial imperfection with a maximum value of E naught at mid height. So I can write it initial imperfection like this. So the initial imperfection serves like a primary eccentricity. Remember the previous slide? The only difference is in the primary eccentricity case we showed E as constant along the full height. Here E is maximum at mid height or whatever is the reality, and E is 0 at the supports, and the analysis is similar, the behavior is similar. You can solve this problem, and that is the kind of behavior you will get. This is, so the real column takes a deflected shape like this. There is an initial imperfection eccentricity of E naught and it follows that path, and asymptotically it hits the P critical line. Is it clear? So this is all general theory, and you can work out the maximum total deflection, which is E naught plus delta m, and you get an interesting result. You get what is called an amplification factor. At least you should remember this. The amplification on the deflection that you get, which you compute elastically, is 1 divided by 1 minus P by PE. P is the load you apply, P is the Euler buckling load for an ideal column. So this kind of amplification you will encounter. Obviously when P is equal to PE, what do you get? You get unbounded deflections. That does not happen, the material is going to fail before that. But does it make sense? In other words, I am giving you an equation for that line, an approximate equation. Omega is the amplification in your deflection. Okay, now we come to our real topic, which is beam columns. Okay, we looked at pure columns to understand what buckling is. We are now looking at beam columns, and most of our problems P is not very high, but still we want to know what's the maximum P it can take. So we are looking at a beam which is subject to lateral loading. Could be a concentrated load, could be a UDL, could be end moments, could be anything, but also having an axial load. How do we find out the behavior of such a beam? If P is 0, what is delta max? W L cube by 48 EI. If you remember the formula, W L cube by 48 EI. Do you think it will increase when I put P? How much do you think it will increase? By that factor which we looked at, that's a good guess, by omega. 1, okay, that's a good guess. 1 divided by 1 minus P by PE is the increase I will get in deflection. Actually you can prove it. So let's do that. So you can write the equation, solve that equation, put the boundary conditions, write an expression for delta, find out the maximum value at the midspan. Let us normalize it with the static deflection for a non-slender case. So delta naught is WL cube by 48 EI. So if I take that ratio, delta max by delta naught, and I simplify, how do I simplify a tan function? I expand it in a series. What's that series called? The Taylor series, but in this case it's a Maclaurin series, right? So you expand it, also you expand mu L squared, and when you make those substitutions, you can find out that that series approximates to exactly 1 divided by 1 minus P by PE naught. So that's a good guess. So it really turns out to be what you guessed, that omega. So that's a factor that it gets magnified, the deflection gets magnified, and if you were to plot it, it will look like this, which means I am plotting the magnification factor on deflection, which is omega, on the y axis, and I am plotting the P by PE naught on the x axis. When P is equal to PE naught, I get infinite deflection. When P is 0, I get the WL cube by 48 EI. That means the factor is 1, otherwise I can find out. So this makes sense. Okay. Now I am also interested in bending moments, because as a designer it's not deflections that really matter to me. How much does the moment get magnified? Now please understand, what is the bending moment at the midspan in a simply supported beam? WL by 4. Will that also increase, Ashish? Will that also increase? When I have axial compression, will the moment also increase at midspan, WL by 4? The deflection increases by omega. Will the bending moment also increase? It will increase, right? So that's what you're going to look at. Why will it increase? Let's be very clear. This is a statically determinate beam. statically determinate beam, your midspan moment, will it not always be WL by 4? Whatever you do, plus P delta is what you do in second order analysis, that is what you should say. In first order analysis, the answer will not change. Even if you had material non-linearity, it will not change. WL by 4 remains WL by 4, even if that damn beam yields, it remains WL by 4. But in the deformed configuration, if you cut a section there, it will be WL by 4 plus P into delta, delta max in this case. Is it clear? And that second order moment will be significant if delta max is significant, and delta max will be significant when either the beam is too slender, which means its EI is small or its span is large, or if P is close to the critical buckling load. Got it? So that's second order analysis. So it's also, this is also known as P delta effect, because you are adding, literally adding a P delta moment to the moment that you got in the undeformed configuration. Does it make sense to you? So it's interesting from a design point of view. Where do you have such P delta moments, in which kind of structures? Commonly, I'll give you a clue. We have an ocean engineering department there. They should be learning all this. I hope they are. No, berthing structures. You must have seen jetties where ships go and people get off. So those berthing structures, which are decks, they are resting on piles which supposedly go deep and ideally should hit the seabed. They are long, slender piles. They are slender, and they can, so they are going to be vulnerable. And let's say there is an impact, let's say a ship comes in, you have ways of reducing the impact, then these columns are subject to lateral loads, then you will surely get P delta moments. So as an engineer, you should know how to calculate P delta moments, right? That is where all this knowledge comes into play. Now if you had a heavy load acting, then that delta is going to be large, and so you have to calculate correctly. Now if the P is constant, let's say that load is not changing, and if you plot delta max by delta naught, you can still do linear analysis. Say, look at this equation, look at this delta max equation. It is a linear function of W and it is a non-linear function of P. If P is constant, you can still do linear analysis, but if W is constant, then you have a non-linear analysis problem, okay? Or if you have proportionate loading, you know what proportional loading? W and P keep increasing in a fixed ratio. So whether to do linear or non-linear analysis depends on which is constant. If you are lucky, P is constant. If your P is constant, you can happily continue with your linear elastic analysis by adding some amplification. But if unfortunately P is changing, either you have a constant W case or a constant W by P case, then you have to recognize that you are dealing with a full blown non-linear analysis, which you can't do so easily. Okay, this is just for your information. Don't worry too much about this, but you can generalize and say, look, if I have second order effects, my maximum deflection will increase by a factor omega delta, my maximum moment will also increase, and that factor may not be the same as the same factor that I have for deflection, so I will call it omega m. Is it clear? And these things have been worked out for different boundary conditions, different load cases. You can find out what is the magnification factor. Okay, now we are getting into the last bit of this topic. Remember, I said introduction, and now we said we will look at beam column stiffnesses. Okay, why do we want to do this? Because we really want to find out what is happening to our 4 EI by L, 2 EI by L, 3 EI by L. That is our real interest. We are now in a position to do that, because in the previous case we looked at a beam with a axial force P and some loading acting on it, and we said if it is concentrated, it is something, it is UDL, it is something, we can work it out. Now we do not put those loads, we apply an end moment. like this case. If I have an end moment MA, okay, and if I didn't have any P, what's the rotation that I get at that end, the flexibility coefficient? It will be ML by 3EI at this end, and at the other end 6CI, right? And your bending moment diagram would look like that. If you had an axial compression, then the theta will get increased, and we won't go through the proof of it, but it will be increased by a function as shown here, and if the other end is fixed, then that 4EI by L will also change. Remember, if there was no P acting here, what would be this value? S is called a stiffness measure, it's 4EI by L, right? And R is the carryover factor, it will be half times 4EI by L. So now can you understand the symbols R and S and S naught? They are our conventional stiffness measures. S naught is typically 3EI by L. We want to know how much it changes when you have P coming into play. S is 4EI by L. We want to know how it gets affected when P comes into the picture. R is 0.5 or RS is 2, it's the same thing, and we want to know how it gets affected by P. So to cut a long story short, without going into the derivation, let's look at the results, okay, because these things can be worked out, and you can prove this, okay. The proof I'll skip. It's an interesting proof, it's explained in great depth in the book, you can go through it, you can work these out, the carryover factors, etc. Let's look at the final picture. So they look like these, you know, if you have a spreadsheet, you can really write down for any P value, for any mu L value, you can write down those factors. But let's see what it looks like. It looks like this, okay. On the x axis I have a parameter mu into L, which can be expanded as square root of PL squared by EI, okay. And on the y axis I have that ratio stiffness divided by EI by L, and when one end is hinged, the answer is 3EI by L typically when there is no actual force acting. Is it clear? Now look carefully, look carefully. When I have no actual force acting, it's 3EI by L. When I have some actual force acting, it reduces, and it reduces to 0 in fact when the level of actual force is what? You can see that, no, it's hitting 0. When will that be? When you have, that's the limit, when you have the asymptotically, when it hits a pure buckling case for a simply supported beam. Is it clear? So listen carefully. If I have a simply supported beam, I apply an end moment here MA, then if I want if I want a unit rotation, the moment that I need to apply here is going to be 3I by L if my axial force is 0. If my axial force is the critical buckling load, then I can really play with it like plasticine, because it yields completely, so the stiffness drops to 0. Is it clear? If I am applying P, which is much smaller, small value, then I really don't have to worry, because you see it's kind of tangential at that initial value. Can you see this? So I need to really worry only if it crosses, the mu L crosses 1, because I can really ignore. So I take a call on when I can ignore and when I cannot ignore. Is it clear? But what happens when I apply a force? Mathematically I am getting a value even when it crosses the value of pi, is it not? That value is pi there, 3.14. Why do I still get a solution? Well, mathematically you will get a solution because you get a negative value of stiffness. Okay, that's what the equation does. What does the negative value mean? It means your rotation and moment are in two different directions, which you will encounter if you had a rotational spring there. It's very interesting. Okay, so it can take some more load till it hits the critical buckling load. For this case, of a propped cantilever. Okay, so this is just incidental, so it can take some more values and that's the maximum it can take. Is it clear? You don't have to worry about the negative portion, that positive portion is good enough, but if you want the big picture you will get this also. This is for the case of a simply supported condition. We will also now look at the propped cantilever condition where you need S and R, and S starts with the value of 4 EI by L and RS starts with the value of 2 EI by L. As you apply axial compression, 4 EI by L will drop gradually and it is going to hit 0 when you have the critical buckling load, which is that propped cantilever case. Remember, we 2.045 pi squared EI by L squared, and R picks up very slowly. RS is almost 2 all the time, and then if you keep applying more loads you can get some more results, okay, which are only of more theoretical interest than otherwise. Is it clear? So we have these functions, these are called stability functions, S, R and S naught. They are a function of a parameter called mu L. That's all you need. You can write, you can program it. So if you give me P, if you give me L, if you give me EI, square root of PL squared by EI is mu L. That's my parameter for figuring out what is this stiffness measure. The stiffness measure will be related to 4 EI by L, 3 EI by L, 2 EI by L. Is it clear? So to sum up, you can write a table, you can make a table and generate these values, and you have a different story when you have tension. Instead of axial compression, if you have tension, there is no question of any buckling happening and your stiffness is actually increased. So you also have equations. One way to check out is when you solve the equations, you get hyperbolic functions. Actually you get the same function with a, instead of cos you get cosh, C-O-S-H. Instead of sin you get sin, you sin here, tension is sin, okay, S-I-N-H, and you get tan H and so on. Is it clear? So this is just by the way. If you have chord rotation, and we will finish with this, if you have chord rotation, then if you have a simply supported case, do you think the chord rotation will cause any curvature? Pin, support settlement, do you think you will have any curvature? You don't get any curvature, but will it affect, will you have any forces? Yes, you will. To satisfy equilibrium in the deformed configuration, you get now a vertical force. So what's your net axial force? It's not going to be P anymore because you have vertical reactions in the deformed configuration. So it's going to be the resultant of P and P phi AB. Phi is your chord rotation, right? So if it's in compression it will look like this, if it's in tension it will look like that. Just remember this. Okay, if you have a pinned fixed condition and you have a chord rotation, you have a curvature, and you can prove that you have n moments which are the same n moments as you got earlier. Instead of 3 EI by L, you write now S naught. S naught is the replacement for the correction for 3 EI by L, in which you include the effect of P. Is it clear? This is same as what we did earlier. Just remember, wherever you had 3 EI by L, you now start using S naught, and wherever you had 4 EI by L, you have S, and the carryover will be RS. So you have S into 1 plus R. Instead of 6 EI by L squared, you will write S into 1 plus R. That's all you need to remember, and the fundamentals are still the same. Okay, you can work out everything. So instead of 12 EI by L cubed, you will write S into 1 plus R divided by L into phi. Okay, but you also have plus or minus phi AB, P phi AB in the deformed configuration. We will end with this last relationship, which is an important point as an engineer. Let us say I have a problem of buckling. Okay, I have a column, I want to increase its buckling strength. What should I do? Laterally supported. Okay, so shall I, if I have a pin joint, shall I put a support in the middle? Okay, will it solve the problem?
Effective length decreases.
So will my critical buckling load get doubled 4 times. Why will it go 4 times? Because of L square. Okay, but that demands an infinitely stiff brace, right? KB should be infinity. No, no, you have to answer a question. Should KB be infinite or not?
No.
Huh? I don't want buckling to take place. I don't want that joint C to move. So KB should be infinite. Can you make an infinitely stiff brace? Not possible. So be practical.
Put a spring.
Huh? No, no. So you can prove, you don't need to do this. You don't need to do this. You have to provide a minimum stiffness for that brace, and that will guarantee this for you. Let's check it out. Okay, let's say you provide a weak brace, low value of KB. How would you think it will buckle now? Okay. If I put a hinge there, then definitely it is going to buckle like this. Can I find out the minimum value of KB needed from this picture? How do I get it?
Equilibrium.
Just equilibrium, you're right. Just equilibrium. You will get a reaction there. If I take the free body, which is 2p phi, when I solve that equation, that's a force in my spring. So if I have a spring with a capacity greater than that, it will not happen. So that's how I get KB. So practicing engineers have figured out a way of finding the minimum stiffness you need for a brace, but this is when you cleverly put a hinge there. You had a pin joint. If I don't put a pin joint, then also will I get the same answer? Yes. Can you prove it? So we look at so this is the answer. The minimum stiffness needed is 16 P naught by L. You can prove it, which is, if you substitute the value of P naught, which is 2 pi squared EI by small l the whole square. Small l is the, in this case, half the total length, right? So how do you prove it? So let's look at this. I am not putting a hinge in the middle. Okay, today is a little long session, but let's finish it. We are almost there. We're going to score the goal now. Okay, we have a low stiffness. It's going to deflect like this. Got it? You have high stiffness, it's going to deflect like that. The answer for this we know. This is going to be 4 times, right? I want it to deflect like this and not like that. How do I do it? Well, I can prove it from first principles by solving this equation that anything is possible. I can write my equilibrium equations, I write my stiffness values. You understand, you can do an equilibrium study of this, solve the equilibrium equation. Here you have moments coming into the picture which was not there when you had the hinge, and the moments are related to your stiffness measures. So plug in those values, and if you substitute all those equations, solve the equation, it takes a little while, it's explained in the book, you will get an interesting result. The interesting result is you can find the critical value that it turns out to be exactly the same solution. Okay, because it's getting late, I am not explaining this to you, but a quick look at this graph. This stiffness of the brace, when it is 0, I don't get any capacity. As I keep building up, it at some point it will buckle like it will buckle with a negative sine wave, or it will buckle the other way. It will always buckle at the lowest load. So this is the mode shape that I want, the second one, KB minimum, okay, because it can't take, it will buckle at this rather than the other, but this is enough for me to achieve. I have 2 sine wave curves, reverse sine wave, I have got the stiffness that I need. So for practicing engineers, these kind of fundamentals are very important, and it's especially important when you have a very long column. You can work out what the minimum bracing needed. It need not be infinite, but you have to provide appropriate stiffness to make a long column behave like a relatively short column to increase its. This is the introduction. Tomorrow we will have a quick look at slope deflection method, and finally we look at matrix method. Thank you for your patience.